Okay, so the presentation is organized as follows for today. I would like to introduce model uncertainty and model adaptive management. I will first talk about the key elements that we need to be aware of when we try to solve an adaptive management problem under model uncertainty. We will go into the details of what a Markov decision process looks like. I'll introduce an example, the Gaussian fit example. It's a conservation problem, and we'll have some discussions. And then Paul will do a little bit of MDP solve demonstration. Okay, so for those that can't remember what happened yesterday, fair enough, it was late or early. Let's start by reminding everyone what adaptive management is. So in many domains, we do not have access to the dynamics of a system, but still need to make decisions. And this is what adaptive management is about. Adaptive management is learning by doing. So we select decisions to achieve a management objective that I put in the center here. And what we want to do is find the best management decisions while simultaneously gaining information. So there's two types of uncertainty. Parameter uncertainty, reminder. So the hidden variable, the things we might not know that are important to actually select our best decisions and influence what will happen in the future. Things like survival rate, growth rate, probability of success are what we call uncertain parameters, and they take infinite number of values potentially. We can discretize them, and then they can take finite number of values. And number two here is model uncertainty. That's what we'll focus on today. The competing scenarios, sea level rise, examples, and expert opinions. They a broad description of what will happen in the future. And in that case, the hidden variable takes finite number of values. So why do I go on about finite number of values or infinite number of values? It's because it does affect the way we will, one, choose the sufficient statistic, and two, solve a problem. So we've seen that yesterday. I want to remind everyone that at any time you can, so there's two types of ways of solving adaptive management problem, the active adaptive management problem, which is the optimal way, and the passive adaptive management problem, which uses makes the assumptions of certainty equivalence. So that means what we know, we assume that what we know now won't change into the future when we make the decision, but we will learn outside the optimization loop. And so session one, focus on that green part. Session two will focus on the other part. Well, session 6, sorry, focus on. So Paul will talk a little bit more about that. And I have this area here that is in blue, which actually allows you to switch from, let's say, the infinite or parameter uncertainty side to the model uncertainty side. So you can solve a parameter uncertainty adaptive management problem as a model uncertainty adaptive management problem. So we'll talk about that too. Okay, next. So as I said, at any point in time, you can solve a passive adaptive management. So I guess on that figure, if it's too hard to solve an active adaptive management problem, you have the option of solving a passive adaptive management problem. So it is a heuristic, and basically it's equivalent to solving a Markov decision process. I will talk about that a little bit at the end of this class if we have time. So what we're interested in today is solving the active adaptive management. So the learning is included into the optimization. So let's think about that. What does that mean? So active adaptive management requires thinking ahead. So if we want to include the learning into the optimization, we have to think about all the consequences of all the possible values of the unknown information before deciding the optimal action. So we have to think ahead. If I do this action, what will I learn, and how will this influence my optimal action, and how do I choose the best action based on the objective I have? So it's quite involved. It's not that easy, as you can see. It's a massive, basically, it's a massive tree of futures that we have to think about. A little bit of history about adaptive management tools to reduce model uncertainty. Well, I did a bit of reading, and the first paper I could find was Silvet in 1968. He was using adaptive management under model uncertainty in the fishery literature, and the seminal book by Walters also includes a few examples. So there was a bit of activity here, maybe about 10 papers maximum, and they all try to solve that problem in different ways. Very interesting. It's very interesting because they didn't have computers at the time, so a lot of the work, high-performing computers. It's not that long ago, but a lot of the work was actually about understanding, interpreting the results, and trying to guess why the solution would look like that. So that's very interesting read if you have time. And then in the mid-1990s, it's all this work that was implemented by the US Fish and Wildlife Service about the harvest quotas of waterfowls in the USA. And so that's in collaboration with the USGS crew, which I think some people from USGS are online too, and some people from US Fish and Wildlife Service are online too. So that work was actually very influential for developing new adaptive management approaches and programs. So there was a lot of papers about that application. I think they've done an excellent job at reinvigorating that field. And then in the 2010, there's more works coming from Australia and still work going in the US. And we've seen, and now I'd say there's between 20 and 30 papers, or what I know of, people that have applied adaptive management. And some of these papers are about more reducing model uncertainty in conservation and resource management. Okay, so what are the key points to design an adaptive management to reduce model uncertainty, or in the case where we have model uncertainty? So this is my inference diagram here. I remind everyone that what we observe is a state of is the state space ST here. That's our species of interest or population, and over time it evolves, and our action usually influence that ST+1, and our objective is linked to we usually want to maximize some kind of maybe a profit function, or if it's a conservation problem, we're trying to get our population as high as possible. So our issue is that we know that we're not able to specify that probability transition just based on ST and AT. We're missing an important element, which is our hidden variable here, that influence that transition probabilities. Therefore, we're not sure. We're not sure about our success over time. So what we need to know is learn about YT, or in a way maximize our resources, including the fact that we can learn about YT, maximize our objective, including the fact that we can learn about YT. Okay, so let's talk about YT. It's in the case of model uncertainty, it represents some plausible alternative hypotheses or models. So if you think about consequences of sea level rise on migratory shorebirds, as we've seen yesterday, the consequences of sea level rise, if we have just 0 meter, are different for birds, are different than if we have 2 meters. So this is the type of alternative hypothesis that we want to articulate. And so that's the first work you have to do. This could be different population dynamics or different hypotheses. Expert opinion works too. But you need to come up with this information, and it's a very difficult part of a problem. in itself, these models, they can take many forms. What we, from an optimization perspective, or decision-making perspective, is we want to be able to have access to what we call the transition probabilities that we've seen for Markov decision processes for each of the possible model. And so this is what I write here. This is the transition probability for model Y of transitioning from ST plus 1 to ST, from transitioning from ST to ST plus 1, given that we have implemented action 80, right? And we can rewrite that as a conditional probability, that form, and I'm just using an index there, so that it's shorter. Okay, so this is what we need. We need that information there. So as long as you're able to specify this transition matrix, so they also correspond to our transition matrices for each model, then you are good to go. And it's not necessarily easy to do. You might have to run, if you have a simulation model, population dynamics, you may have to run different scenarios. But I'd say intuitively, the reasons why you're doing a model uncertainty problem is because you have different scenarios about the future. So you have different hypotheses about how your threatened species will respond. So typically in conservation, it's quite easy. We don't have a lot of data, so we do simplify things a lot. We had 3 futures for a species and a conservation problem. Either the action works, so the conservation project is successful. So it's like we get a good results. We increase the population dynamics, or it doesn't. So it's a decrease of a population, or it stays the same. We can't really see any changes. So worst case scenario, there's really 3 possible futures in conservation. So that can help you define these transition matrices. So as we saw yesterday, we use belief states as sufficient statistics. And belief states are probability distribution over states. And so that's my way of representing that belief states. So it tells us where we think we are. It's our current knowledge, and we can update it as we go. So in the context of adaptive management, active adaptive management, the optimal decisions depends on our observable state. So let's say the state of a population and the value of that belief, where we think we are, which model is most likely to be true. Important information. This time the policy or strategy is defined as pi. So it's a function of S or belief, and it matches our action and an action to do. What we're interested in doing here is finding the optimal strategy or optimal policy. So because our optimal policy depends on knowledge and what's going to happen in the future, to do a good job at optimizing, we need to augment the state space from S to S and a belief over our model Y. And to find the best action, I'm going to go into the details of the model just in the next slide, I believe. But to find the best action, or to maximize our objective, we have 2 options that I know of. We can solve a Markov decision process with a continuous belief state space. So that, one of the issues we have with that probability from an optimization perspective is like these elements are continuous. So you can solve a Markov decision process with a continuous belief state space, and that's what we look into today. We call that a belief MDP. Or you can solve a pro-MDP, and we'll see that in day 4. They're quite similar, but they use different algorithms and make different assumptions, and they both have different challenges. So, okay, so this is, so we say we have to augment the state space with a belief state. So let's look into the details. What is our new way of defining our adaptive management MDP for model uncertainty. So a reminder, when we just have a Markov decision process without uncertainty about the dynamic of a system, when I say without, I mean, we do have transition matrices, but they're stochastic, but we actually know what the values of these probabilities are. Okay, so for a Markov decision process where we know these transition matrices or states, we have a state space or action space, transition matrices that provide the dynamic of a system. It's very important. It allows us to calculate our expected future reward and our reward function. But as we saw yesterday at the breakout session, ST, AT, so they depend on the state, but they can also depend on the action of a discount factor. In that case, the optimal policy or strategy is a function of S to A, right? So we just need to know what states we are in, and we can find the optimal action. And the way of calculating and the way of ranking or evaluating the performance of each policy is through the evaluation of what we call the value function. That's the it corresponds to the expected. In our case, it corresponds to the expected sum of rewards over time. Okay, so now let's look at the changes. What occurs when we account for model uncertainty and we augment the state space. So now we have our states becomes our observable state space. So let's say our population abundance, for example, and our belief over which model is the true model or probability distribution over the model. Our actions stay unchanged. Our transition matrices could be there's a different way of representing transition matrices. I prefer representing them that way. So let's go with that, but I'll talk about a different way of representing it later on. So the transition matrices, one transition matrix per set of per model. So probability of ST, probability ST plus 1 depends on the state we were previously at time t, the model that is true, and AT or action that we're implementing. So you can imagine, sorry, the small note, you can imagine that as the number of models increases, we're going to have a lot of transition matrices we'll have to deal with. The reward function RST80 doesn't change. I don't think I've seen a problem where it was dependent on YT, but it can happen, and it's fine if it's the case. It doesn't change much. The optimal policy is a function of S, B, and it maps an action A. Our value function that we'll look at is our expected performance of a given policy or strategy. Is now a function of S and our current belief. Okay, so S is finite, and B takes infinite amount of values, so it's a continuous state space. So here's our issue. It's difficult to evaluate to find the optimal action when we have a continuous variable. Okay, so I want to zoom into the optimal value function here. So one way of finding the optimal strategy, what is the best action we should implement given our current knowledge and our states, is to solve the Bellman equations directly. And yesterday we saw what it looked like for an MDPs I think in a matrix form. And so this time I want to expand that Bellman equations in the case where we include that belief. So the red elements here is what changes when we have to account for model uncertainty. So let's start from the left side here. So our optimal value function is a function of the states and our current belief, BT. And it's optimal if it maximizes that term in the middle that corresponds to our expected sum of cumulative reward can be discounted in that case. Okay. So there's two terms in that equations. The first term is the expected immediate reward, so it's immediate. And the second term is the expected future discounted reward. So immediate means time t, and future means in like t plus 1, basically this little thing there. So let's start with the first element here. So when we didn't have the belief, we were sure, like we didn't need to account for the fact that we didn't know exactly which model was true. In the case where we don't know which model is true, so we have a probability distribution of the model, we need to weight the immediate rewards by the probability that each model is true. So it's relevant where it's particularly relevant when the reward is a function of y, right? So I'm just going to add something there. I think I should. Up. So y. Oh, look at me. Is that y? Let me try again. Here we go. Doesn't work, that thing. I don't know how Mike does it. Okay, it's a y. Everyone, okay. All right. And then the second term is the expected future discounted reward. So we want to account for all the future states. So that's a classic. If you remove the BT1, the summation over the y, everything that is red, it's the classic MDP Bellman equations. As soon as we include y, we also have to think about what will happen into the future for each model. So this is why we include the probability transition here for each model. And that's, in itself, this is fine, easy to calculate. That term is easy to calculate. It becomes more complex here when we have to include the optimal value at ST plus 1 and BT plus 1. And so BT plus 1 is our future, where we think we will be, what we think we will know into the future. So that's the complexity of that whole equations. That's what is hard to calculate. Okay, so now I want to step back a little bit and reflect. So we have some equations, but it's hard to see what's happening here. So let's go with a graph. So in the case where we have an MDP, let's say for the model 1, our value for optimal value function is 1 when we are in state S1 and 2 when we are in state S2. And for model 2, we have a different we have a different optimal value function, and let's imagine we have different actions. Let's not care so much about the action. I want to focus on the optimal value function. In the belief MDP world, what happens is we have a probability of a model 1 and model 2. So we have a belief over these ones. And that belief is represented here, right? So this is a belief that model 2 is true, let's say. When we have 0, that means that model 1 is at 1. And when we have 1, that means that model 2 is true, right? And in between is, so on the side, if we're here, on the side, we have a lot of certainty about where we are. But if we are in the middle, it's very uncertain which model is true. So it's the first thing I want you to understand, right? So on that axis, the x-axis represents our belief, and it's continuous, right? Then on the y-axis, we represent the value function in this case S1, because I've assumed we had 2 states, and S2, right? So that could be, let's say, low abundance and high abundance for a species. Right. So what are the other interesting, I'm going to ask the attendants, what else can you, looking at this graph and this information there, what else can you say about the property of the optimal value function for a belief MDP under model uncertainty? See if you find it. Just go for it. There's some, and it's okay if you don't get it. It's okay. Just write something if you can. Yeah, I'll give it another 30 seconds. So I'm interested in some intuition about what this optimal value function represents when we compare it to the normal MDPs function where we don't have uncertainty. Okay, can you please repeat the question? Yes, I was just pondering. I'd just like you to tell me what is remarkable on that. What are the properties of that value function here, right? Okay, yes, why is it not a straight line? Excellent. Okay, so that's the first property of this value function, is that they are convex, and they are they can be approximated by lines if we want. So this corresponds to like lines. We call that piecewise linear convex. Okay, so that's an important property because we can do interesting maths with an optimization when it's convex. And then we have two high values, right? If we look at it on the side where we are certain. So when we are certain about which model is true, that corresponds to either one side or the other side. Here we know that on that side here, we know that model 2 is not true. So it is model 1 is true. And here, model 1 is not true and model 2 is true. So we have a belief of 1 probability. Does that make sense? Okay. So if we know that the models are true, this value function here corresponds to these values here. I'm not very good at that. Correspond to the values of model 1, and these values here corresponds to the values of model 2. Does that make sense? It's because we are certain that when we are at 0 here, then model 1 is true, and we are at 1 there, model 2 is true. So it makes perfect sense that the optimal value corresponds to the optimal value of a MDP for each model. Right, that's the MDP for each model. Maybe it wasn't clear. Sorry about that. I hope it makes sense. Did it make sense? Should I start again? So it's like, why do we care? It gives you an intuition that this makes, I'm trying to get you the intuition that this makes complete sense on the side. And in the middle, that's where it's hard to, that's where it becomes hard to actually find the optimal action and calculate the optimal value function. So I guess in the worst case scenario, what I'm trying to tell you is that if you know how to solve an MDP, you already know what your optimal management strategy is on the extreme point for each state. So it's kind of good news. Why is V equals 1 better than V equals 2 for model 2? Okay. All right, let's make clear that up. Okay, so I'll start again. I think I did a poor job and we have time. So in the MDP world, without adaptive management, So one of his model will be true. Okay. So let's say model 1 is true. We can solve it using an MDP, and we get this optimal value function. We get 1 and 2, right? 1 is for the value of the optimal value function. Depends on your starting state, S1 and S2, right? And for model 2, it's a different alternative scenario. If we were to solve the MDP, then we get a different value function, S1 and S2, right? The issue is we don't know which of his model is true. So, and it's important for our management action and outcome. So we have to solve a belief MDP where we include our models. So this time we don't know which one is true, so we have a belief of other models, right? We have to belief over Y, right? So we have a probability for each model to be true. This can be, for example, if we don't know anything, no prior, we're in the middle, 0.5 here. And so because, so that value function here says this is the value, this is our expected cumulative reward if we for starting state S1 and for any given belief B. And so this would be 0.5, this would be 0, and this would be 1. And so that axis here represent the belief that model 2 is the probability that model 2 is true, right? It's the correct belief. I just need to represent one belief because we can get this the probability that model 1 is true just by putting it 1 minus belief model 2, right? So if I get just one information, I get the other one. Make sense? Okay. So then, what I was the way we would read that graph is that for the when belief of model 2 equals 0, that means that model 1 is true. And so if model 1 is true, we have the optimal solution by solving that MDP, right? And so we get the same values. We get the 1 here that we have here, and the 2 there, then we have 2. If we are here in 1, that means that model 2 is true, and we already know the solution for model 2, right? There's no uncertainty. It's a solution, it's an MDP, so we know that. There we go. So here's the intuition. The intuition is it's easy to calculate that value function when the belief is 0 or 1 for any states because it's just solving an MDP for each of the model. Well, it's hard to calculate it's what's in between. Does that make sense? All right. Any questions? I'm not sure if can you, yeah. It's okay if you don't get it, it's not critical. But I was trying to be like really trying to explain the intuition of this value function, I guess. I can't hear anyone, you know what?
The only question that's up there now, it says, maybe you already answered this, but do the shapes of these curves on the right change depending on whether model 1 or model 2 is actually true?
So they actually represent, so they represent whether this is whether model 1 or model 2 is true, right? Like here, this is where we don't know whether or not model 1 or model 2 are true, right? This is really annoying. I don't know how Mike does it. Obviously, has a better setup than I have. Okay, so this is where we are uncertain about which of the model is true, right? So if we're at 0.5, no idea where they are. So they don't, once we calculate the optimal value function, they don't change. If you don't have the optimal value function for each, it's for each, I guess what I should, for each strategy here, you would have a different curve, I guess. But for the optimal one, there's only one, that's a very important property. There's, once we have a max, that is it. This is the maximum. This is the best value function. This is the best performance. So if you have a different, if you don't get the right strategy, if you get the wrong action, you will be below that. You won't perform as well. You would be below that curve, right? If you don't get the right actions, you would be below that curve. Any additional question?
I don't know if you answered this one about what, maybe you did a minute ago and I'm not sure. What about v = 1 being better than v = 2 or something like that? Because for model 1, I don't know.
Yeah. So I actually don't understand that question because I tried to re-explain the value there. So I think there's confusion about, you know, what this value are, this value, why are this value function important, and it's because this is a way of calculating the optimal policy, right?
Right.
So
Yeah,
what?
somebody asked the question, you know, where does the value function come from?
Yeah. Yeah. So this is the value. Okay. So it's similar, I guess. If you don't remember what happened yesterday, I should have reminded everyone of that. Sorry. Then there's a big gap there. I agree. So the value function is all expected. It's the value function represent the performance of a given policy. So for each, once we have a policy, so once we have our decision rules, so for each state we know what action to take, and let's say we're interested in finding the one that is optimal, so the best one. A value function evaluates the performance of a policy. So if our objective is to maximize, let me give you some intuition. If the objective is to maximize a profit, you want a policy that will have that will give you the highest number of dollar, right? So this and because it's stochastic, it's going to be an expectation. So on average, this will be the your maximum gain, right, for that given policy. Right? In what's difficult, and so Paul tried to explain that yesterday, is a lot of to find this optimal policy. There's different approaches, but the Bellman equations give us. The Bellman equations are the key. Is a key way of actually finding this optimal, the ones that are optimal, the optimal value function, right? And so that Bellman equation for NDPs, you just remove everything that is red, and that's basically the expected sum of reward. So this is like, if I were to write it, and I hope that's gonna work, V star for a given policy, well, the one that is optimal. I'm gonna try not to, for a given state. So let's say we're gonna call it S0. That's the expected sum, and we use a discount factor here of rewards over time. S. So if you do infinite time horizon, it's an infinite here, and that's our reward function. Okay. When we apply our optimal strategy, right? Phi of S. Make sense? It's not well written, but that's like a discount, a summation over time, t equals 1 to infinite, and it's the sum of reward, and I'm missing a little t here, for all the states And that should start at 1, I guess. Yeah. Up.
Iadine, there's also a question that asks which is the best model, 1 or 2. I think the answer to that is neither. Right? In your case, model 1 is maybe good if you believe. Let's see. Model 1 is good if you believe that the excuse me. So model 1 is good in.
Yes, that's right. So
Model
model
1 is
1,
good in the second state, and model 2 is good in the first state. So
that's right.
neither model is better than the other in some sense.
That's right. So exactly. So the value of model 1 is higher here than the value of model 2 there. Can't get it there. Yeah, exactly. So this is why it is an adaptive management problem, because there's neither of the models is superior to the other model, right? Because if a model was superior in performance, we wouldn't have to worry too much to anyway.
There's one more question. I don't know if
Yeah.
you answered this about why is these graphs convex? When you have these graphs of the value function, why is it convex?
That's right. So it's a property of this function here. So it says, so RS, if you just look at the this expected immediate reward, this is a sum of weighted linear value, yeah, weighted linear functions, right? So it's a property of this is a nice thing about Markov decision processes in the partial observable or adaptive management context. If you write it that way, then we have a convexity, a linear convexity approximation that holds. Yes, excellent. So Gwen is suggesting a better way of explaining what I'm trying to say. She says, she got it. The plot is the solutions of a Bellman equation across the values of B. That's correct. So that's a plot of this information, and that's across the value of B. Thanks, Gwen.
One more thing. One person said, are they always convex because of something like Jensen's inequality?
So I didn't look at the proof, but I guess to me it makes sense because if you, yeah, I didn't look at that proof, but to give you some intuition. So also we're maximizing, we're not minimizing, right? And we have these are rewards, they're not cost, right? So so I'm not sure if Jensen inequality would explain the convexity of the optimal solution of the optimal value function. But there's I think who provided, well, that's Armstrong, Astrom. But Angstrom in 1968, it's an old paper, it's proofs of convexity of partially observable Markov decision process, which is, we will see tomorrow, is equivalent to solving a belief MDP of this form, right? And it's because it has this form, right? Okay, should we try the next slide? I'm sorry if I was confusing. I just, I hope you got something out of it. I was just trying to demystify, but I may have confused everyone. Okay. All right, so the remarkable aspect is like it's convex, and on the side here, we are certain that one of the model is true. Therefore, if we've calculated the MDP before, then we should get exactly the same values on the extreme points there for each of the states, right? Okay. And so, yeah, so to solve that equations, it's not that easy, right? Because so continuous MDPs are computationally hard to solve, and approximate solution techniques must be used to derive solutions. So there's very rare cases of exact solutions to continuous MDPs, belief MDP. It only happens if you have a very small problem, a very small number of states and a very small number of models, for example. So a natural way to overcome this limitation is actually to discretize the continuous belief space and to solve it as a discrete space MDP. So it's kind of a good news. I bothered you with that continuous state space, but really, you can discretize the belief state space by a range, like let's say if you just provide a grid or 0.1 or something, and then you end up with a normal MDP. So a discrete MDP instead of a normal MDP. Right, so I want to touch, so basically, this concludes what I wanted to say about solving belief MDPs. And I want to touch about the case where we solve passive adaptive management MDPs very briefly, because in some cases we can't really do it. We can't really solve an active adaptive management problem. So I just remind everyone, in the active form, we were including the learning within the optimization. So that changed our Bellman equations. For the passive one, the learning is just outside. So we don't include it into a stochastic dynamic programming equations. So what it looks like, we fix the belief at every time step. And our optimal value function in that case still represent what we know now. So we still have a weighted sum of rewards here. But if we look at the value function here, we don't need to think about how the belief will change over time, right? We don't have the need to know what our value function would be when we learn. So that's the main difference, and that's where all the complexity was coming from, is because our value function was a function of a variable that was continuous. Okay. Any questions on that? So it's much easier basically. So if you know how to solve an MDP, just a discrete MDP, you should be able to solve a passive adaptive management. So it's good news. And so that allows you to decide, have the best management action. You would then monitor, so get the information, which state do you end up with, still update your belief. So you get a new belief, but it's outside the optimization loop. So you just apply Bayes theorem. And then you can solve again the stochastic dynamic programming. So solve again that equations. And so why is that appealing? In some cases, problems are too hard to solve. And then sometimes we may want to wait several years before we actually learn, or it doesn't make any sense to update your belief straight away or to include the belief into the equations for the learning part. Okay, so I just want to go through an exercise, and I hope it'll clarify everything we talked about. So the application here I want to talk about is maximize the high persistence states of a Gaussian Fitch population over time. And it's also the breakout, it's part of a breakout session exercise number 2. So we'll start explaining what this problem is about. So the Gaussian finch is a threatened bird. And in the case of Northern Australia, in the Kimberley, managers are looking for solutions on how to actually manage that bird. So we have a choice of several actions, and for several for all of these actions, we were able to get the transition matrices. So one of the actions is do nothing, and if I were to represent these transition matrices, so unlike Paul, this is from, so this is ST and this is ST plus 1. So this is different from what Paul represents, uses, and others uses in the MDP. So just so you know, but this is what it represents. So don't focus too much on its probability transition. So this says that it has a high change in CM in low persistence if we do nothing. And if it's in the high states, high persistence states, it has 50% chance of going too low, right? So it's not looking really good if we do nothing. So then if we assume that we actually have transition matrices for all the possible actions that manager could implement. So here we have a choice between doing nothing, managing fire and grazing, removing feral cats, or providing nesting box. So if we assume we had information there, that becomes just a Markov decision process. And we can actually find the best action for each state. And this is what it could look like. This is a policy graph. This is a nice way of representing, instead of representing a function PSA, this is a state transition representation of the optimal strategy. So in low, we would do fire and grazing. And because the outcome is stochastic, we could stay in state low with 0.58, or we could go to fire and grazing with 0.42. If we transition to high, then the best action becomes cats, managing feral cats. And so same thing, you can stay in that state or you can go back. So I just want to talk about this little policy graph in MDP solve. If you've looked at what, if you remember, you can get that information. You can get that information almost. I think it's called P stars in using POMDP solve. So then you just have to draw that graph basically, but you have all the information there. Okay, so that's the the simple world of simple or ideal world when we have a lot of data and we know exactly what's happening for each action. So that's an excellent that would be an excellent position to be in. The issue is that it is rare to know the efficiency of actions when managing endangered species, and so golden finch is one of these issues. There's lots of interactions, competitions between birds, and then there's also other species that interact into the system, diggers that may actually influence or reduce the activity of cats. And so it's very unclear to manager what is the best action and how the efficiency of these management actions would actually improve the chance of achieving our goal here, which is maximizing persistence of a Gaudian finch. Okay, so that's where adaptive management becomes useful. In that case, we can define and elicit a set of plausible models. So I'm going through the process. And the way we did that in that context is asking expert opinions. So one of the things we do when we define this set of plausible models, and then we do assume that the real model, that we don't know what the real model is actually one of these models or be close enough to one of these models, right? So it's a very important assumption, and we'll talk about that a bit later. So we're uncertain about which model is the real model, but we can observe the state perfectly. So we have access to low state or high persistence state of a Gaudian finch. So we ask for experts to provide their state transition matrices, and so each of them went through that process. Expert one, like it's a summary, but like fire and grazing. So each of the experts actually prefer a different opinion, but there's expert 1 and 4 tend to agree. And so in that case, because we don't know which expert is right, we use this belief state to represent where we think we are at any time. So usually when you start, you assume you have no prior information about which expert is right, 0.25, 0.25, okay. And over time, what we will do is like be more confident about which expert is the correct expert. So here we have a higher weights or higher probability that expert 3 is correct or closer to the true model, right? So to help our managers designing their adaptive management program, we can provide some guidance and help them finding what is the best conservation action to perform for every combination of states of a species, so high or low, and combination of belief in models. So as we know, this belief changes over time based on what we observe and what action we've performed. Keeping in mind that our objective is to maximize species abundance in that case, or species persistence, right? So we solve that problem, and I just want to show you what happens when we implement the optimal policy. So when I was talking about the value function, I was explaining how to calculate that optimal value function, and now we are one step further. We've been able to extract the optimal policy, and we want to apply it. We want to simulate it. So to actually derive some kind of insight about what experts should do. So we want to explore what our solution is saying. And because that policy is often quite difficult to understand, a good way of getting some insight or interpretability is to simulate scenarios. So the way I've done that here is I've assumed, and the optimization doesn't know that, but I've assumed that expert 3 was the true model. And I'm testing the strategy, the optimal strategy, the optimal adaptive management strategy, while the simulator simulates draws from expert 3 transition matrices, right? But I guess the optimization doesn't know that. Okay, so we start with a uniform distribution over the belief in expert model. We're here. And the state of the system is low. We can't see it, but it's low. And the first actions that is recommended for that combination of belief states 0.25 across all experts and its state low, I think, is fire and grazing. So let's say we go one time step, implement fire and grazing. We draw from the true model. The simulator draws from the true model, and we get some outcome. We stay in low. So the next step is to actually learn. So we've done a management. We're getting some information. We're doing our monitoring, and now we learn. So we have to update our belief based on that information. And this is what our new distribution looks like. Expert 3 is a little bit ahead, not too far with expert 2. And then we continue. We look at the optimal management strategy, and it says you should manage cats. And we simulate that, we implement the action, we get a signal. This time we're getting a high response, high persistence, so there's a bump. Update our belief again, and when cats are favored, that's basically expert 2's model. So we get higher confidence that expert 2 is right. And we continue, try cats again, it seems to be a winner. Boom, we get a bad response. So it's a stochastic systems, right? So it's something you need to realize that it's not because you're getting a good response one day to an assumption that means you are right in the management you're deciding. So, and again, so it doesn't work, then we try fire and grazing, so and keep going like that, and we keep rolling and implementing our belief. And as you can see, we go high and up and downs. We struggle to find whose expert is the best, and then we've tried fire grazing cats, and then suddenly the optimal policies suggest it's not working somehow. Yeah, suggest the nexting box, and that is, it took him about, he started doing next about time step 7, so took him 7 time step to actually find that was expert 3 that was closest. That was the true model. And because it's stochastic, there's some low here, and so the optimal policy also probes. So it's like, oh, maybe I'm wrong. Let's try fire and grazing again. So it's not a straight line. Okay, so that's a simulation of how you would implement an optimal management strategy for model uncertainty. And as I said, and we'll talk about that, the work of actually solving and coming up with an optimal strategy is just really 1/3 of the work. What's most important is making, from my perspective, is actually making sense of what the strategy recommends and how checking that it makes sense with managers. All right, so we we've shown how to solve an active adaptive management problem using a discretized belief MDP in the context of model uncertainty. So this discrete approach is also relevant for parameter uncertainty, and we talked about that. It's particularly convenient when we don't have a sufficient statistics, and we can discretize our uncertain variable into finite number of values and then go back to basically model uncertainty. So it's a nice switch here. I just wanted to highlight that. And it's done a lot in the literature, and you can check all of these papers if you're interested. I want to talk about some important caveats. So an important caveat is when we use model uncertainty, we do assume that one of candidate models we include is close enough to the true model, right? So we, it's really hard to know what will happen in the future. So what my recommendations is really think about all the potential future, what could happen. So typically for conservation of a threatened species, we have 3 possible future, or perhaps just 2. Either it works, like the management action works, we get a good results, or it doesn't. And if you wanna include I don't know in the middle, you can. So think about everything that could happen into the future and make sure your candidate models, your set of models you include, actually cover all the possible futures, so that you don't have you're not blindsided by the fact that your optimization hasn't included all the futures, and your true model might be something completely different. So don't be overconfident on that aspect of a modeling. So what's important to know is that the computational complexity is actually proportional to the number of models that you're including. So it's that trade-off that you have to account for. And I want to talk about the objective too. Like the objective in model uncertainty is to maximize the expected sum of rewards, so that can be discounted. Not to find out which model is true, right? This is not, the objective isn't to find out which model is true. It's about maximizing the management outcomes. And so this value of information aspect to adaptive management. So if we find the optimal action and don't find which model is true, it is okay, because we would have maximized the sum of rewards, right? So you need to have a lot more data and to be accurate about which model is true in that case. It's a difference with parameter uncertainty that we will see with Paul. So it's important to see that. It's because we are in the discrete space and we don't include all models. I also want to touch on value of information. So the models you are included must be different enough to require alternative optimal management strategies and outcomes. Because if you include models that have the same outcome, there's no value of information, right? So it's very important to first solve the MDPs that are attached to each model and check whether or not if you get it wrong, what is the value of information. So there's papers that have done that, but you can just do it by hand, intuitively. Just check whether or not the optimal strategy is different, and check whether or not the performance really, if they're not different, does the performance is really significant if we get it wrong. And so this question, obviously, there's other issues when we include too many models. So there's this thing about we want to be close enough to the truth. So we want to be we want to include as many models as possible, but complexity depends on this number of models. And then it doesn't help if we include models that behave in the same way or provide the same management outcome. So there's all this question about, okay, but how do we select the minimum set of models? So the way I go about it is I really focus on what it means for a species or what it means for a management outcome. So is it working or it's not working? That's how I deal with it. And I also ask my experts, tell me all the future scenarios you think could happen. The one that are most likely, but also let's talk about the one that are less likely. And we talked about the macro property yesterday. Again, we are making this assumption here. Might not work when we have delayed benefits or complex life cycles and population matrices. I want to emphasize the need to actually work on the interpretation of your optimal strategy. So you can optimize everything you want, but if it doesn't make sense, we won't go very far. I made these mistakes before. I thought, one of my first experience was just solving that problem and say, yeah, I'm done. And then 2 years later, I was still struggling, interpreting and explaining the results. And so for adaptive management, we have optimization techniques, but they provide guidance for managers or end users. And it's very important that we try as much as possible to include and communicate why this is a good action at the time. There we go. Paul, I'm sorry, I'm 10 minutes behind schedule. Do you think you can take over? We can just pause while we switch slides. And we can just check, we can check with the audience if they have questions. Something didn't make sense.
I think Paul has been answering a lot of questions in the I don't, if there's anything that didn't get answered, it looked like maybe Paul was busy answering questions. So they were asking about uncertainty and the reward. And again,
yep. Yeah, it's possible to have uncertainty about the reward. That's completely correct. Yeah. And also there's different ways of representing these equations. That's my way of representing equations. So I think the principles are here, and Paul will talk about how we interpret that in how we put that together in MDP solve. I'm just curious if the example, I'd like some feedback about the example, if you thought that the Coolidge-Finch example was helpful, or the simulation was helpful to see how it works.
Somebody's giving some feedback about the Finch example was helpful.
Okay, so maybe next time I'll start with the Finch example and then get into the equations. Sorry.
Yeah, good. Okay. Thank you.
Thanks, everyone. There's a question from Brian. Are there techniques we'll discuss that output not only the optimal action, but also the next best one? I could see situations where the best action may not be possible for a particular year in the future. Okay, so I think it's a two-part question. Are there techniques we'll discuss that output not only the optimal action, but also the next best one? Yes, they are. So the policy graph I was talking about, the graph that shows you what to do, depending on what you observe, is actually one way of representing what is likely to be the next best optimal action. So it's a state transition graph. It can get quite complex with beliefs if a problem is quite difficult. And then when you say, I could see situations where the best action may not be possible for a particular year in the future, that seems like you should probably include that into your model. Yeah, you should probably be aware of that when you calculate, when you try to provide some recommendations. And so, yeah, it's probably a discussion you need to have with the managers you're working with, or and try to see what it influences.
This question came up in a project I was involved in, having to do with prescribed burns, and one of the researchers was concerned because the managers didn't always follow the burn recommendations. And what we tried to do then is to build in the rationale for why the burns wouldn't be why the recommendations wouldn't be followed. So that became part of the system behavior.